Welcome back everyone, and this is another exercise on system Verilog constraint. And in this exercise we have to write constraint in such a way that one out of two variables should be one hot code at a time. What I mean, let's say we have two 8 bits variable, so two 8 bits signals, and let's call them A and B. So my aim is to write system Verilog constraint in such a way that during the randomization of the class, only one of them will be one hot code, and it will be random. So if A is one hot code, then B will not be the one hot code. And if in the next repetition loop or in the next simulation, if B is one hot code, then A will not be one hot code. So how to do this? So let's begin. So I will write a class, and like every time I will name it cons1. I will name two variables and I will randomize them, so I will use the rand keyword before them. And let's take bit data type, and both of them will be of 8 bits. Let's call the first one as A, and let's call the second one as B. So our aim is to achieve the constraint in such a way that either A or B should be one hot code. So for that we have two ways. So in the first method I will use another selector variable, and using that selector variable we will put a constraint which will determine that either A or B will be one hot code. So let's create another rand variable, and it should be of 2 bits. Let's call it select, or SEL in abbreviated form. So first I will write a constraint for select, and you will know why. So what I will do, I will write a constraint for select in which I will make select one hot code. So I will use $1 hot code, which is provided by system Verilog, and I will put select inside it. So the possible values after every randomization run of select will be either 0, 1 or 1, 0, and we will use that to determine which one of them will be one hot code. So my next constraint will be for the major signals A and B. So I will write another constraint, and I will call it main underscore C. And here what I will do, I will concatenate the one hot code of both A and B, and then I will assign it to select, and you will know why. So first let me write it. Okay, it's one hot. So what I'm doing, I'm concatenating the one hot code of A and B, and I will be assigning it to select. And remember, since we are writing system Verilog constraint, you should write 2 equals 2 operator. So here what will happen? So basically, onehot code returns in basic system Verilog code. Onehot returns a single bit value of 1 or 0. So if onehot is 1, then of course that particular targeted variable or signal will be onehot. If it is 0, then it will not be onehot. So in constraint we have to write a comparison. For example, in here we could have written 1, which means the same thing, which says that the onehot of the select should be true. So here we are concatenating it, and since onehot expects a 1-bit variable and we are concatenating it, and in total it will become a 2-bit value, and we are assigning it to another 2-bit value, which is select. So what will happen? What are the possible values of select? The first possible value of select is 0, 1. So what will happen if select is 0, 1? If select is 0, 1, it just means the value will be assigned to the concatenated onehot of A and B. So onehot of A just a second. So onehot of A will get this value 0, and onehot of B will get the LSB, which is 1. So this is what will happen when you will assign it to select. And what is the other possible value of select? It is 1, 0. So what will happen if the value of select is 1, 0? The onehot of A will be 1 or true, and the onehot of B will be 0 or false. So at one time either A or B is going to be a onehot value, and it is because the select which determines that what will be the value assigned to the concatenated A, onehot of A and onehot of B, because it is itself a onehot value. So it has only two possible values, and as per its possible values, either A will be onehot or either B will be onehot. So this just proves our constraint and it will work. So without any further delay, let's begin with our test module. And before that, I will write a void function to display the value of A and B and select. I will print the value in binary so that we can see whether the value is onehot or not. And I will also print the value of select. Since we are done with our class, let's go ahead and write our test module. Let's declare the handle of our class, which is cons1, and let's call it c1. Let's begin with our initial block, and let's assign an object to our handle. So I will use the immediate assertion to randomize the class or the object, and if it fails, then it should show an error. So with everything done, without any further delay, let's hop on to our QuestSim window. And here, first I will just compile the code. Okay, we don't have any errors, so I will go ahead and start the simulation. Okay, we did run into some errors. One hot line number 12. Okay. Okay, it is just a typo, and we should add dollar here like we did for A and select. So hopefully this should resolve the error. Let's compile the code again. Let's start the simulation again. Okay, you could see the result that since select is 1 0, the 1 is getting assigned. So here what will happen if select is 1 0? If select is 1 0, then one hot of A will be true, which makes A one hot value. As you can see it right here, that it has 1 in its second most significant bit, and remainder of the bits are 0. And other than that, what will happen when the LSB of select is 0? One hot of B will be 0, which is clearly evident right here. So what I will do, I will put this assertion inside a repeat loop, and I will run it multiple times, let's say 10 times, and let's check few different results. So I will run the compilation again. Okay, we have few different results right here, and you could see that when the MSB of select is 1, A is one hot caught, and when LSB of select is 1, B is one hot caught. So here select is 1 0, and we have a one hot caught value for A, not for B. Here also select is 1 0, and we have another one hot value for A. And here also select is 1 0, and we have another one hot value for A. And here select is 0 1, and here A is not one hot, only B is one hot, as you can see it right here, it has 1. And here again select is 1 0, so A is one hot, B is not. Here select is 0 1, so here B is one hot and not A. Again you could see it right here that select is 1 0, A is one hot right here, select is 1 0, again A is one hot, and here also select is here select is 0 1, so here B is one hot, A is not one hot, and here select is 1 0, so A is one hot and B is not. So this is how you could write a system Verilog constraint in which if you have, let's say, two signals or even more than two signals, you could allow only one signal to be one hot at a time. So there is another way to carry out the same task, and that particular way is more minimalistic. So I will show you right here. So that particular way does not even require another select random signal. So I would just comment it, and I will also just delete it, or I will comment it. I will comment this also. Okay, here it does not matter. So what I can do, I will also comment this, and I will also comment this. So we could carry out the same task just using a single constraint. And I will again call it main underscore C. And to do that, first we will write a concatenation of one hot chords of both the signals, just like here. But this time, since we don't have uh, any select signal, we will not assign it to any other signal. So first one hot of A, then one hot of B. So after we are done with the concatenation, what we will do, we will one hot the concatenation of the one hot of both A and B. So what I will do, I will put it inside a round bracket, and here I will write another one hot which will supersede both of them. So what I will do, I will write one hot. So what will happen? So one hot returns a single bit value, as I have mentioned right here. So this one hot will see the concatenated value of the one hots between A and B as a 2-bit value. So it will see the value inside the round bracket as a 2-bit value. So this particular one hot forces that either A will be one hot or either B will be one hot. So the possible values will be either this or this. So what will happen when the value is a 2-bit 10? So if this is the case, just a second. So if this is the case, so it will be very similar to what happened right here. So here, if it forces that this 2-bit value to be either 10 or 01, then one hot of A in this case will be 1, and one hot of B in this case will be 0, which just simply means that A will have a one hot value and B will not. Similarly here, one hot of A will be false or 0, and one hot of B will be true or 1, which again means that B will have a 1 and one hot value, and A will not. So without any further delay and with our new modifications and even more minimalistic code, if you could just delete it out, let's start another simulation. And here I am checking the code whether everything is fine. Yeah, this should work. So let's compile the code again. Let's start the simulation. Let's run the simulation. Okay, you could see it right here that with our 10 repetitions in which we randomized this class, either A or B will be one hot, which is same uh, as our previous implementation. So here in the first case, A has a non one hot value and B has a one hot caught value. Here B is one hot caught, A is one hot caught, and B is not. Here A is not one hot caught, but B is. Here again A is not one hot and B is. Again A is not one hot and B is. Here also B is one hot. Here also B is one hot. And even here also B is one hot. In the second last output, A is one hot and B is not. And again in the final output, A is one hot and B is not. So doing the concatenation of one hots between A and B and doing one hot code of concatenation of both of them, we could achieve the same functionality using the constraints. So this could be a tricky question and could be asked in interview. So I hope you find this video useful, and I will put the link of the code in the description. So stay tuned for more. Thank you so much.